Hello everyone, welcome to Electric Motors course. In this lecture, we will discuss the numericals on a three-phase induction motor. So here is the numerical. A 440 volt, three-phase, 50 Hz, 4-pole star connected induction motor has full load speed of 1425 rpm. The rotor has an impedance of 0.4 plus J4 ohms per phase, and rotor to stator turns ratio is 0.8. Calculate first one, that is full load torque, second one full load copper loss, third one maximum torque and speed at which the maximum torque occurs, last one is starting current. So here we have an induction motor, that is the input to the induction motor is 440 volts. It is running at 50 Hz frequency and the speed of the motor is 1425 rpm. So let us list the given data. Frequency is given, it is 50 Hz. Number of poles are also given, it is 4 poles. Speed of the motor is given 1425 rpm, and rotor impedance, that is Z2. So Z2 has, it is, you can write this as R2 plus JX2, so which means R2 is 0.4, X2 is J4 ohms. So now here we need to calculate the full load torque. Motor is running at full load only. It is mentioned that it is running at full load. The speed is 1425. First we need to calculate the full load torque. The torque equation, first one we need to calculate the full load torque. Let us write the torque equation for induction motor. Full load torque will be equal to constant K. The K constant is given by 3 by 2 pi into small ns. Small ns is the rotations per second, synchronous speed in rotations per second, into the slip of the motor, full load slip, into E2 square into R2 divided by R2 square plus SX2 whole square. So this is a formula we use to calculate the torque of the induction motor, that is full load torque. So here to calculate this full load torque, we need this ns, that is rotations per second, synchronous speed, and full load slip, E2 rotor induced EMF, and rotor resistance. Rotor resistance is given, R2 is 0.4 ohms, and we need X2. X2 is also given, it is J4 ohms. So let us calculate one by one. So first ns we will calculate. Ns is equal to, it is the capital Ns divided by 60, that is rotations per minute divided by 60 will give us the rotations per second. So to calculate ns, the formula is synchronous speed, it is 120 F by P. So F is given 50 Hz. Number of poles are also given, it is 4 poles. So if you calculate this, you will get this as 1500 rpm. So if you calculate the ns, you can calculate the ns by this form, ns divided by 60. Next we will calculate the slip, that is full load slip, and the rotor induced EMF E2. So slip, the formula for slip is, it is ns minus n divided by ns. Ns we have calculated, it is 1500, minus n is given 1425 divided by 1500. Upon calculating you will get this as 0.05. In terms of percentage of slip, it is 5%. Now we need the rotor induced EMF E2. So to calculate E2, they have given the turns ratio, that is rotor turns to the stator turns, that is termed as K, which is equal to rotor turns is E2 per phase, stator turns is, it is E1 per phase. So this is given as 0.8. So E1 per phase, the E1 per phase voltage is equal to the applied voltage. Applied voltage will be in terms of line quantity, so we need to convert the applied voltage into phase voltage, that is EL divided by root 3. If you do it, you will get the phase value. Applied voltage is 440 volt divided by root 3, you will get the phase voltage. So from this equation, E1 phase is known, K is known, E2 phase we can calculate here. So E2 phase, in general we will just write it as E2 while substituting in the torque equation. So this will be equal to E1 phase into 0.8. So 0.8 into E1 phase, where E1 phase is the 440 divided by root 3. So this will be, upon calculating, you will get this as 203.227 volts. So this is the E2. So now we have calculated the E2 slip, NS, R2 is given, X2 is also given. So by substituting all the values, we can calculate the full load torque of the induction motor. The full load torque, upon substituting all the values, we will get this as 78.88 Newton meter. This is the full load torque. Let us go to second question, that is we need to find out the full load copper losses. Full load copper losses. So to find out the full load copper loss, we need the current in the rotor windings, that is rotor currents. Rotor currents we represent by, under running condition it is I2R, which is given by slip times E2 divided by Z2. Slip times E2 divided by Z2 under running conditions. Slip we already know, it is 0.05. E2 we have calculated, it is 203.227 divided by Z2. We need to consider the magnitude. So magnitude of Z2 will be equal to square root of R2 square plus R2 is 0.4 square plus SX2 whole square. So S is 0.05 into X2 is 4 whole square. So if you calculate this, you will get the I2 or running condition current, rotor current under running condition will be 22.721 amperes. So this is the rotor current. To calculate the copper loss, full load copper loss, the formula is full load copper loss. Copper loss depends on the current flowing through the windings. So the current flowing through the rotor winding is I2R. So it is I2R I square R. So rotor resistance is R2. Since this is a 3-phase machine, so the total copper loss will be 3 times of the I2R square into R2R. So this will be, upon substituting all the values, we will get the full load copper loss as, it is 619.518 watts. So this is the total copper loss of the induction motor. The third one is, they ask to find out the maximum torque, and the speed at which it occurs. So we need to find out the maximum torque, and as well as when the maximum torque occurs in the induction motor, we need to find out the speed also. So let us see the third one. We need to find out the maximum torque. The maximum torque equation is again constant K, that K is 3 divided by 2 pi into small ns into E2 square divided by 2x2. The condition for maximum torque is the slip should be equal to R2 divided by x2. When this condition satisfies, we can achieve the maximum torque in the induction motor. And if you substitute S is equal to this R2 by x2, we will get this equation. So if you substitute all the quantities, E2 we know, x2 we know, ns we know, so we will get the maximum torque of the induction motor. So upon substituting, we will get the maximum torque as 98.6 Newton meter, and the slip during maximum torque condition is R2 by x2. R2 is 0.4 divided by x2 is 4, so the slip will be 0.1. This is the slip under maximum torque condition. Now once you calculate the maximum torque, it is also asked to calculate the speed at which it occurs. That is, the speed we need to calculate when the maximum torque occurs. Let us take the speed as Nm. The equation for speed in terms of slip and synchronous speed is ns into 1 minus s. This s is nothing but maximum slip under maximum torque condition, that is Sm. So if you substitute all the values, slip ns is 1500 into 1 minus Sm is 0.1, you will get the speed as 1350 rpm. So when the motor is delivering maximum torque, the motor is running at 1350 rpm. The last question is, we need to find out the starting current of the induction motor. What is the current drawn during starting, we need to find out. The starting current of the induction motor can be calculated by using the formula. Starting current IST is equal to, it is E2 divided by Z2 during starting. During starting, the speed of the induction motor will be 0 and slip will be equal to 1. So that's why there will be no S term in current. Under running condition, you will get it S term. So this E2, we already know it is 2.3.227 divided by Z2. We need to consider the magnitude here. So Z2 without any slip, it is 0.4 square plus 4 square. So upon calculating, the starting current will be equal to 50.554 ampere. So this is the solution of the given problem. Thank you.